something. Oh,
30.
30. And thank you very much to Omer for very kindly hosting, and Andrew for his usual wonderful set of services putting the whole thing together. And in fact, the first speaker is Omer, who needs not very much introduction, but what I should say is there's one word that kind of describes what he does for a living. And anyone entering the building that hasn't figured out what this one word is, please put their hand up. Erlang. Erlang. So he does it, and he does everything to do with Erlang. And tonight, of course, he's talking about something else really, which is
completely different.
Which is speeding it all up for fun, and he says for profit, and I'm waiting to see what profit actually means.
Not much profit, unfortunately, but yeah.
Speeding things up. Okay, so I'm going to give you a timer, and off you go.
Hi folks, I'm Omer. I do Erlang really, but I'm actually a hardware engineer, so this talk is going to be completely about electronics and squeezing performance out of them and so on. Before I start, I'm sure everyone remembers the horrible blue LED crisis of 2005, where we had to stick, LEDs, or sorry, rather fans with LEDs into our computers for no reason, whatever. And then it got worse, and we had to endure the horribleness of these ultraviolet reactive fans. Pipes with water cooler radiators and stuff like that. And then things got really out of hand, and people started experimenting with liquid nitrogen and even liquid helium. Only to find that it's actually a very bad idea. You do not want to do that to your motherboard. So today, really, in the 15-20 minutes, we're going to look at, in 45 seconds, how the computers work. Silicon devices and overclocking, what do we do to overclock them? It's really in the title, really, there's really not much to it. Concepts, what do we do to overclock these devices, and challenges. Now, the profit bit is about Bitcoin, which I'm sure most of you are familiar with. So we're going to look at how we can overclock a Bitcoin miner. And then I'll talk about this little guy called vftweak, that little circuit board I designed. Haven't tested, unfortunately, didn't have the time to simplify, hacking hardware. So this is what a contemporary computer program looks like. It's a set of instructions. So you instruct your computer to execute these instructions that do something. In this case, it just prints something to the screen. Now, your CPU, again, the contemporary CPU, looks a bit like this. A lot of things are emitted in this. This is just a simplified diagram. But the heart of this is that corner over there. It's the fetch, decode, execute sort of section, which grabs the instructions, decodes them to figure out what it is, and then just executes them. Keep in mind, this is all synchronous logic. Synchronous logic means that basically all the instructions are synchronized with a clock pulse. So this is, you might have heard of I2C or SPI. These are common protocols people are using. And here, SCL is the clock for I2C, SCK is the clock for SPI, and so on and so forth. So you can see that there's a pattern. If you look at SDA, for instance, at a few clock cycles, data stops. You have the stop and the start byte and the acknowledge, etc. So what this means is that theoretically, if we increase the clock speed of the device, it will go faster. And indeed, that is the case. But you can't just keep on increasing the clock cycle because there are limits as to how much you can do that. Let's talk about shiny silicon. So this is what your CPU looks like, or your electronic processor, any kind of processing device looks like. Modern devices are manufactured using extremely small process technologies. We're talking about nanometers, which is 10 to the power of -9 meters. And this is a cross-section of a transistor. And the future sizes we're looking at are 25 nanometers, 35 nanometers, and 47 nanometers. So as you can imagine, these devices are far from perfect. So one transistor that you have on one side of the device is not going to be equal, or the characteristic B is not going to be exactly the same as the one on the other side. So in order to sell these devices, the manufacturers obviously have to provide you with specifications. And the way they do that is they test a bunch of these devices, and then they characterize them into what they call bins. So, for instance, if you buy FPGAs, you can buy different versions of the same chip with what they call speed grades. So speed grade 1 is the fastest, it's rated to run at X megahertz, and speed grade 2 is slower than that, and it runs at X minus Y megahertz, and so on and so forth. But most commercial microcontrollers that you buy, they don't really bother with speed grades that much. They just say, here's a table, the maximum external clock frequency that you can run is 31, or rather 20 megahertz or something along the lines of that. What this means is that you can actually squeeze quite a bit more out of these devices most of the time by pushing them into, uncharted territories almost. What that means is the operation of the microcontroller or the processing device that you use are not guaranteed at those frequencies, but it should, to a certain extent, it should be okay pushing them 5 more megahertz. You might find that 2 devices out of 5 would work quite happily at 40 megahertz maybe, but the other 3 might not like going above 25 megahertz. And usually overclocking, I'm now talking about little embedded boards that you can overclock. That can simply happen by replacing either the crystal or the oscillator, or by hooking it up to a clock source of some sorts. Modern motherboards on computer systems usually allow you to programmatically tweak this. So you can say in your BIOS maybe, you can say, oh, I'm going to increase the clock frequency by this much. But if you're working with a small system, you should be able to just replace the crystal and then have it running on the fastest speed. As I've mentioned, this doesn't, you can't just keep increasing the clock speed though. One of the main reasons for this is the clock skew. Now, if you consider the fact that modern processing devices, modern CPUs, consist of millions of transistors, and the fact that these millions of transistors are packed into a certain amount of, certain region, you can imagine that even though it's optimized, there's still, a finite amount of time between one signal going from one end of the chip to the other. Now, as we mentioned, these devices are not perfect devices. They do have load capacitances that vary, and also manufacturing tolerances means that you can't generally predict them to 100%. Well, you can't predict them 100%. So there's, even though if you simulate it, there's still going to be variances and so on. What clock skew means is that the clock pulse that you have coming into your system might arrive at different parts of your synchronous logic at different times. Now, given that in an ideal synchronous system, each operation should happen at, say, a clock pulse, if the clock pulse arrives at different points in time, then obviously you're going to have a bit of a trouble. So if you find that, overclocking your 200 megahertz CPU to 500 makes it do funny things, this probably is the reason why. This is the main reason why overclocking doesn't really work after certain speeds. Now, there is a way to overcome this to an extent, and it's called overvolting. Now, providing more voltage to a CPU does not magically give it more juice to go faster. What it does is it increases the drive strength of signals. So by increasing the drive strength, you can theoretically minimize the effect of clock skew. Theoretically. Another issue, of course, is we're dealing with very small geometry sizes, and dissipating heat generated by these devices, these transistors, from a very small area is becoming a problem. It's simple physics. The surface area is extremely small, or rather very small, and you have to get rid of quite a bit of heat dissipation. this is why you see people resorting to extreme tactics such as liquid nitrogen and so on and so forth. In a normal system, you should... We have more visitors, it seems. Come on in. Anyway, so you really should not have to, you shouldn't have to resort to liquid nitrogen. Most of the time it should be, a good heat sink in a fan should be okay. Okay, so that was the theoretical overclocking part, which I'm sure most of you are familiar with anyway. Let's talk about a practical example, and Paul, this is the profit part for you. So Bitcoin, it's crazy. It's at the moment something in the region of $1,000, right? Can we get an update? A real time. So you can buy these Bitcoin miners. Essentially, these are devices that $1,177. Wow. So these devices basically perform lots of calculations, hash calculations to, make you rich. That's not always the case, especially with these little guys. You really can't, even making return on investment is very unlikely these days because the network difficulty of Bitcoin is extremely high. That's another topic, we can talk about that later. But people are taking these really seriously. You can see banks and banks and banks of these devices being deployed. By default, these run at 300 mega hashes per second, I think, or 333. And if you look at the circuit board, it's actually fairly simple. The chip you see on the far right is the actual ASIC miner chip itself. And over here you can see the crystal that is driving that chip. There's some interface logic around here. And another important part in these sort of little systems is the voltage regulation, buck boost regulator part. This is a buck regulator that goes from 5 volts to 1 point something volts. And generally, you have two parameters that you can change in these systems. The first one, of course, is the crystal. But before I go to that, because this is an extremely niche or specific chip, there isn't a data sheet. But this is the actual manufacturer talking about how they could be overclocked and what they've done in the past. So the first attack vector is changing the crystal. Luckily, it's just a very standard 5mm by 3.2 millimeter crystal. You can just order one and desolder it and change it. But as we've discussed, after a certain frequency, you will need to increase the voltage to increase the drive strength of the signals as well. And that's where you have to dig out the data sheet for the buck regulator. So this is a fairly simple arrangement. By changing the ratio of R1 and R2, you can increase or decrease the voltage going into the ASIC chip. And that is the formula to drive it. If you look at the circuit over here, luckily these R1 and R2 values actually correspond with the data sheet. So if you just replace R1 with something else, you can get a different voltage value at your ASIC. And someone actually went through a lot of experimentation and provides you with this table. This is the clock frequency or the crystal frequency that you introduce to your system, and stable voltage that's required by the ASIC, and the value of R1 resistor that you need to hack, basically. So changing those two parts is an easy task, really. You can just desolder the oscillator and then change the resistor. But I was thinking, how can I maybe programmatically do this without having to desolder things and solder things back in again? So on a very boring flight to Krakow, I started designing this little circuit. And basically, the idea behind this is that it has a programmable oscillator that allows me to go from 5 kilohertz to 66 megahertz. Going to 66 megahertz is probably a very bad idea on that particular circuit. It has a digital potentiometer that you can use to change the resistor values on the buck regulator. And there's also an analog to digital converter to figure out what sort of voltage we're actually getting on the output of this chip. And because I'm somewhat paranoid, I also included a temperature sensor because I wanted to, see how hot or how cold this was running. Now, I've just a couple of minutes ago, I pushed the design files to a solder pad, but I also have some PCBs. This is an untested design, I didn't have time to solder one up. So if you're brave enough to play with this, come and find me after the talk and I'll give you one of these things. The form factor of this, it looks kind of funny, but it actually, once you solder the temperature sensor on it, you should be able to directly put this at the back of your ASIC miner, or your Bitcoin miner. I don't recommend you buy those things anymore because they're, extremely, they're not very powerful, but they cost about £10, so, good fun playing with them. So, I think that's about it for the moment. I'm going to write some scripts to actually control this at some point in the future. I don't know when. But yeah, the idea is extremely simple. You should be able to hook this up to other designs that you have, even designs that you're developing, and you should be able to use this as a little multi-tool to look at how it responds to different frequencies and different voltages. So just imagine having this little command line tool that will allow you to set resistor values and frequencies easily. That's what we're aiming for, or I'm aiming for. If you're interested, find me and I'll give you one of these PCBs. So this is probably the first time in the OSHUG history that I finished early. If you have any questions, I'll be happy to answer them. Thank you.
Yeah. I've got one. I've never seen a digital pot before, so...
They're amazing. So that particular chip has two, and you just have A, B, and wiper. Just works exactly as you would expect a pot to be.
And you can put whatever voltage on it and stuff like that.
Within reason.
Within the supply rails,
yeah, within reason and within the supply rails, particularly the supply rails.
Okay, question. I can't believe it.
Omer,
Hey.
leaving aside the for-profit, a lot of what I do in my spare time is trying to excite school kids. I'd quite like to apply this to sort of things like a shrimp and see how far you can wind a shrimp up.
Atmega 328 are extremely hackable, so it would be a fun experiment to do.
Come get bored.
Oh, definitely. I have like 5 or 6 that anyone can have, so let me know if you're interested. And again, I started putting together the little code or command line utility, but life got in the way, so yeah, as usual. Cool, I think. I'll be here if you... Oh, Andrew.
Could you use it on a D0 nano?
You can. The clock cycle, or clock chip that I put in there has, I think it works at 3.3 volts only. And you can tweak a certain few parameters of it. But it should work fine with a simple FPGA. Generally, they do have 3.3 volt oscillators as well. Be careful overvolting FPGAs though, especially the ones that are not programmed. Static power consumption it can get very messy. Can get like that.
The chip's not soldering itself, that's what he's not worrying.
That's, yeah. I think Xbox had that problem where people were actually reflowing them using T candles.
In your experience of overvoltaging different ICs, how often do you find that you lose them irrevocably?
I like to push them really far, so I do have to have my hot air station on at all times most of the time when I'm playing with it. But most of the time, especially with like Atmel microcontrollers, you can push them really hard. For instance, there are certain features of these devices that only work at certain frequency ranges. So, for instance, on the ATtiny AT85s, the US I think it's the clocking bit, or rather the timers, that's not guaranteed to work properly. Like part of it is not designed to work at 3.3 volts. It only works fully, or it's advertised to be fully working at 5 volts. most of the time it does work fine on 3.3, and you can
Okay.
actually push it. So overvolting and overclocking is a thing, but underclocking and undervolting is also a thing as well.
Oh, yeah.
I haven't
More worried
mentioned
about-
that, but
more worried about overvolting because I'm looking at a possible one-way situation, right? Where
Yeah.
you overvolt a little bit too much and you no longer have a chip. You know you have something fried.
the most frustrating thing is that part of the chip dies,
Yeah.
and then if you're not watching it,
Yeah.
this happens especially when you're trying to bring up a new design, and you might have some metal things lying around on your bench and stuff. If the part of the chip dies and the rest of the part continues working, that's the most frustrating part, because you're trying to figure out why it's, you know. Also, you solder two boards. One of them works perfectly, the other one doesn't. I've lost quite a few hair bits and pieces, or patches of hair for that.
So the message is, have a big bucket of chips when you do this.
Exactly. Also, have a reference system that's running at optimal conditions, and the one that you're abusing, pretty much.
Yeah.
So always scientific method. Always have a reference.
Is it true they mostly die of heat, so just slap a big heatsink on before you start messing with them?
Yes, starting with adding a big chunky heatsink and some airflow is always a good idea. Most of these new devices, for instance, this ASIC minded chip, sticking a heatsink on the top of it is not actually the best way to cool it, because it's a QFN package and there's a big, huge thermal pad underneath it. So most of the heat is actually dissipated on the circuit board side. So that's why they have a heatsink on the other side of the device rather than on top of the processor itself. So depending on what sort of package you're using, you might have to. Most of the producers, they have guidelines on how to cool these systems. And if you're designing the circuit yourself, you might find that adding a selection of vias near the chip might help reduce the power, the heat. Or it might help with the heat dissipation better than just having, just a ground plane basically. So if you look at, especially power transistors and stuff, you'll see that there are lots and lots of tiny holes near them on the PCBs. That's to dissipate the power, or heat, onto both layers of copper, or more if it's a multi-layer PCB. But then, if you overdo it, then it's not good either. So most of the manufacturers will have guidelines as to how to design these PCBs for you, or rather, for you to read. They don't design them for you.
Okay, we done?